Here's APC 2.1, number 6 and 7. I know you can read, so read the data. Hit pause anytime. That'll probably be quite a number of times. Part A is find the order and rate law. So rate equals the molarities to the proper exponent times K. We're going to have to go find K too. So let's isolate the molarities. If we isolate NO, we choose experiment 1 and 2 so that O2 doesn't change, which means the effect of the rate can't come from the O2. So let's concentrate on 1 and 2. So this increases by a factor of 2, and it generated an increase in the rate of a factor of 4. Take a look at the exponents and make sure that you get that that's an increase of a factor of 4. This times 4 is that. So we get molarity is a factor of 2, rate is a factor of 4. 2 to the something power generated a 4 result, so the exponent is 2. So we could say it's second order with respect to NO. If we want to talk about O2, let's isolate it. If we use experiment 1 and 3, then NO has not changed, and it can't be the cause of the change. This increases by a factor of 2. However, this also increases by a factor of 2, so the exponent there is 1. So here's our rate law with our proper exponents now that we just discovered, and of course it's times K. That's really a lowercase k, in case you're wondering. It kind of, sort of, only barely maybe matters, if at all. Sometimes we use capital and sometimes we use lowercase, and I was never told why. In this case, it's a lowercase. Notice that. So let's go find K. Well, pick any line you want. They picked experiment 1, and it'll give you a molarity, and a rate that were true all at the same time. So by that, we can generate K. Put in the values you found for the line that you used, and solve for K. Now, for the units, what we've got here is molarity per second over molarity cubed. And when we flip this fraction, you know, this is also multiplying by the reciprocal. So what we get is 1 over molarity squared second, which is that. This is our 25 per molarity second. That's the same thing. That is that. Oh, squared, sorry, squared. There. And so you don't actually have to walk through this. This will always be some number per molarity to some power second, and this exponent will be 1 fewer than whatever this exponent was that it was trying to cancel out in the molarity. So if this is a third order reaction, you'll get per molarity squared second. So calculate the rate at the instant when. Well, now we know K, and they're going to give us the molarities. So here's K, and here's molarity, and molarity of this is NO, so it gets a second power. Here's O2, so it gets a first power. And, you know, punch it through the calculator. D, I don't want to mess with because I can't recall that ever coming up on the test, so forget it. On 7. Again, we're doing basically the same thing. So let's isolate H2. Let's isolate NO. If we go line 1 to 2, we throw out the effect of H2 because it doesn't change. This is an increase of a factor of 2. This is an increase of a factor of 4. So 2 to the something power is 4. And again, NO is an exponent, excuse me, of 2 at second order. That's a coincidence. Don't draw any conclusions about NO from that. To isolate H2, let's talk about lines 2 and 3, and this gets a bit more complicated. Notice we can't isolate it, can we? So you have to pick something. But you can't pick 1 and 2 because then H2 doesn't change. You have to either pick 2 and 3 or 1 and 3 so that something changes, right? And they picked 2 and 3, and the answer is because. Honestly, it's got to be something. So just to go along with the pre-printed solutions here, fine, I'll go along with line 2 and 3. Now, this is an increase of 4, which is pretty easy to recognize. The difficulty is it's very tempting to say, oh, this is an increase of 2, but you've just run that backward. You have to go the same direction. You know, from experiment 2 to hop to 3, this increased, or actually, increased by a factor of a half, if you want to call it increase. It changed by a factor of a half. It decreased by 50%. This increased by a factor of 4. The rate also increased by a factor of 1 because it didn't change. So what we have here is the rate, right, is equal to NO to the second power times H2 to the unknown power. Well, we got to solve for H2, or we've got to solve for the exponent, right? And they're still leaving it pretty easy numbers. They don't get deep into this, and you don't have to solve it with logs on the real test that I've ever seen. In fact, I know that's true because I wrote very detailed explanations for 7 or 8 different tests, and I still couldn't tell you how to do it with logs without cheating and looking it up again. So they're going to leave it pretty easy. This is a quarter, though. It's really tempting to say this is 1. It's not. A half times a half is a quarter, is a fourth. If you move this under 1, you get 1 divided by a fourth is 4. When this moves under here, you get 4. So 4 equals 4 to the box, 4 to the unknown power. The exponent is 1. It is first order with respect to H2. So the exponent on NO is 2, and the exponent on H2 is 1. So calculate K. Well, is it the same temperature? Of course it is, otherwise you don't have any good data. That wouldn't be fair. So grab a line, any line. What did they grab? They grabbed where the rate was 0.136, so they grabbed line 1. Here's rate, here's something, it'll be to the second power this time. This will be to the first power. Solve for K. Again, we have a third order. These exponents added up are 3, so it'll be per molarity squared seconds. And again, the units actually repeat their little trick from last time. We, of course, get a different number. And find the rate of appearance. And I mean, you could double check, what was the rate of? Oh, it was initial rate of N2, and N2 is a product, so it's the appearance of N2. So they're not changing anything. That's the rate that they initially stated. That would be pretty weird. In fact, probably impossible otherwise if they change that up. And the rate will be K that you just discovered times the molarities that they said to the appropriate powers that you discovered.